The experiment is conducted in a square environment. A Turtlebot 4 mobile robot uses active inference for perception and control. A stationary beacon, equipped with an NRF 52833 development kit, continuously transmits a Bluetooth low-energy signal. The active inference agent observes the received signal strength of the transmitted beacon and navigates toward its source. This panel visualizes the agent's belief over the transmitter location together with the currently selected model resolution. The proposed method dynamically selects the most appropriate representation from multiple candidate resolutions. The remaining panels display the current step: the active model, the selected action, the observed signal strength, inference latency, available processor resources, prediction error, and the informativeness of the current observation. The proposed method initially employs a coarse representation when the transmitter is far away and progressively switches to finer representations as the robot approaches the target. This transition emerges naturally through meta-inference, allowing the agent to balance localization accuracy with computational cost. In this experiment, the coarse representation is sufficiently informative over most of the trajectory, allowing the agent to rely almost entirely on the coarsest and the next finer representation throughout the navigation task. This demonstrates the emergence of resource-bounded rationality. As the robot approaches the transmitter, the environment becomes increasingly informative, encouraging the meta level to select a finer representation. However, when processor availability decreases, the agent temporarily switches back to a coarser representation in order to maintain its computational budget for each inference step. Once sufficient computational resources become available again, the agent returns to the finer representation. The remainder of the video presents navigation using fixed resolution models throughout the entire task. As shown here, the agent using the coarsest representation is still able to approach the transmitter. However, it continues to wander around the target because the representation is not sufficiently precise to distinguish the transmitter location. With the next finer representation, the agent consistently reaches the transmitter. Nevertheless, the results clearly show that maintaining this higher resolution throughout the entire navigation process is unnecessary, since the coarser representation is sufficient for most of the trajectory. The higher resolution representation also consistently reaches the target, but at a substantially greater computational cost, while providing little additional benefit over much of the navigation. The proposed method automatically learns these trade-offs by maintaining a meta-generative model that predicts the relationship between environmental context, localization accuracy, computational cost, and available processing resources. Consequently, it selects the most appropriate representation online, achieving an effective balance between performance and computational efficiency.